The topic of today's lecture would be collisions. And transport phenomena. These two topics are, of course, closely intervened, just that transport phenomena are enabled by molecular collisions. So before we start, we need to establish some language which would allow us to describe collisions between molecules. So first we are going to discuss gas of identical or almost identical particles in the vessel, and these particles move chaotically with some velocities, and as you know, these velocities are distributed in agreement with Maxwell's distribution, and the collisions happen between them because the number density of these molecules is very high. And the first quantity we want to introduce in order to describe collisions is a so-called collisional cross-section. So you might wonder what this actually is. And let's start first with the concept of just a cross-section. So let's say we have a molecule which can be modeled as a solid sphere of some radius r. And if I cut this molecule by some plane, I would get a cross-section, and that cross-section area would be equal to the area of the circle of the radius r. That is pi r squared. Of course, if we want to describe the collision, this geometrical cross-section is not what we need. We need something, some kind of a more elaborate concept. And in order to get this, I'm going to consider the motion of one molecule in between these two collisions. So first I would assume that all other molecules are fixed in their places. So only one molecule moves while all other molecules remain at rest. So I'm going to draw the points which correspond to centers of this molecule, and I assume that my molecule moves at some velocity v directed as shown in this figure here. So how I'm going to determine whether the collision would happen or not between this molecule and other molecules? Of course, well, let's say that this one has the radius r1, while these molecules which are at rest, they have somewhat other radius r2. Well, of course, I'm going to set these two radiuses as approximately equal to each other, but let's start first with this with this somewhat different model in which molecules have slightly different radius. So the collision might happen if a center of the molecule happens to be at a distance r from the line of the velocity of the molecule which moves, and when r is less than r1 plus r2. So if anything of this happens, then the collision happens. So the set of points in space which are located to a given direction at a distance which is less than some other distance is given by this infinite cylinder. The base area of the infinite cylinder equals to r1 plus r2, and of course I can continue this cylinder further, and if the center of other molecule happens to fall into this cylinder, then the original molecule and the other molecules would collide inevitably. So in this way, it becomes reasonable to assign to the base area of this cylinder, to label it as this letter sigma and call it the collisional cross-section, because this is again area of the cross-section. It's a cross-section of this cylinder in which the other molecule center needs to come into in order to have a collision. So this collisional area, this collisional cross-section is given as pi r1 plus r2 squared. And of course, in the case when r1 equals to r2, when all the molecules are identical to each other, then it can be calculated as pi times d squared, where d is the diameter of the single molecule. Okay. That's the first concept I'm going to introduce. The other one is related to the motion of molecules in between two collisions. We want to understand the length of the path or the distance traveled by a molecule in between two collisions. Of course, the distance is a random value, and we cannot get the distance because in each particular case, these distances would be distributed along with some distribution law, which we are going to establish somewhat further. But the main stuff we need to do is to introduce a so-called mean free path. Mean free path. So that is the average distance traveled by a molecule in between two consequent collisions. And then we are going to determine this mean free path. Okay, the idea is that if we have this cylinder which has the base area which is equal to the collisional cross section and the height which is equal to mean free path, then inside the volume of this cylinder, on average, you would have one another molecule. So that means, okay, how can we determine the number of molecules inside the cylinder? We need to multiply the number density of these molecules by the volume of the cylinder, which is equal to V is equal to sigma times lambda. And that should be approximately equal to 1. So that gives us an estimate for the mean free path, which is 1 over n sigma. And if you check the dimensions, everything would work, because n has the dimension of meter cubic, reciprocal meter cubic, while sigma has the dimension of meter squared. And if I multiply these two, that would give us meter to the minus 1, and reciprocal of that would give me the units of length. Okay, but so far we have considered well, a very special case, quite well, an example which is unrealistic, in which I could consider that only one molecule moves, but all other molecules remain at rest. That's of course not the case in any real gases, and if we include the relative motion of molecules, if we include the relative motion of molecules into consideration, then this estimation would be somewhat corrected, and the correction is by the factor of square root of 2. So usually the mean free path is determined as 1 over n sigma square root of 2. The square root of 2 comes from the fact that if you have one molecule moving with the velocity v1 and the other molecule moving with random velocity v2, then if we go into the reference frame in which one molecule is at rest and the other molecule is allowed to move, then the relative speed of the second molecule with respect to the first one is given by the vector sum of v1 and v2, or actually the vector difference, that would be v2 minus v1. Because if we want to put this molecule at rest, we need to subtract the velocity v1, and after we subtract this one from the second one, then the total velocity will be v2 minus v1. Of course, okay, the direction of this vector is not related to the directions of these vectors. It's some kind of a small mistake in my figure, but that is it. And the average v2 minus v1 average v2 minus v1, the average vector is by square root larger than the average square root of 2 larger than the average vector or the average speed of a single molecule. That applies both to the average speed, also to the mean square, root mean square speed, or any other speed associated with the Maxwell distribution. You can even say that if I go into the reference frame in which one molecule is at rest, then all of the other molecules in that reference frame would be, again, have velocities which are distributed according to Maxwell distribution, but as if the temperature has increased by a factor of 2. So that means that all of the velocities should be multiplied by square root of 2, and that means that the average time between collisions would decrease by square root of 2 with respect to the case when all the molecules are at rest, except for a single one. And that would lead to the decrease of the mean free path by square root of 2. So this is one of the first formula we have derived here. Lambda is 1 over n sigma square root of 2. Well, another important value is not only the mean free path, but also an average time which passes between two collisions, and that can be determined as lambda over the mean speed of the molecules. So the single molecule, if it on average travels the path lambda, then if I divide this path by an average speed of the molecule, and that would give me an average time between collisions. Okay. The next thing I want to discuss is the rate of the collisions in a unit of volume. So we have molecules and they experience collisions among each other, and let's say that we choose some unit of volume and consider all the molecules moving in that unit of volume and experiencing collisions in that volume. So we want to determine how many collisions happens per unit of time in that unit of volume. So rate, okay, per unit of time, so the number per unit of time per unit of volume. The number of molecules in the unit volume is equal to the number density n. And as we know, each molecule experiences a single collision on average in time intervals of tau. So I think it would be a great idea to get the rate of collisions by dividing the total number of molecules by the rate at which single molecule experiences a collision. But this formula is very close to the right answer, but slightly wrong, because we also need to account that in each collision, two molecules participate. So that means that if we count collisions using this formula, then each collision would be counted twice. Once when we count collision for the molecule number 1, and the second time when we count the collisions for the molecule number 2. So in order to account for this discrepancy, we also need to introduce an additional factor of 2 in the denominator. So that would give us n over 2 tau for the rate of collisions. And if I insert tau from here, that would give me a rate of collision of nv average over 2 lambda. Well, all of these are formulas, and you might wonder actually what's the physical scale of these values, so why they are so important in real life, and well, actually how much the molecule travels in between two collisions. Well, there is an answer to that if we consider gas and atmospheric pressure and the temperature at room temperature, 300 Kelvin. And I'm not going to reproduce all of these calculations, but you just need to know that lambda in this case is approximately equal to to 100 nanometer. It can be 60 nanometer, 90 nanometers, 120 nanometers, depending on the molecular weight, depending on the molecular size. While the molecular size, this collisional cross-section, can be calculated assuming that the radius of a single molecule is approximately, well, on the order of 1 angstrom. And if you don't know what angstrom is, this is actually 1/10 of a single nanometer. So that's 0.1 nanometers. So it can be 1 angstrom, 2 angstrom, but something around that. So from this we can calculate the sigma as pi r squared, actually pi times d squared, so that gives the value. Okay, that's lambda. Actually it means that in the standard conditions the molecules travel quite a small path between these collisions. So if you look at this, it kind of looks like contradictory, because when we have established Maxwell distribution and other distributions, we have assumed that our gas is ideal. By ideal, we meant that the molecules almost don't interact. So the interaction force between molecules is negligible, so as if the molecules move independently from each other in the vessel. But it turns out that actually that doesn't happen, because they experience collisions so often that they're allowed to travel about 100 nanometers before it collides with something else. Moreover, actually, collisions play a very important role in establishing the Maxwell distribution and other distributions, because this distance, lambda, is essentially a distance at which you can consider the system microscopic. So if the characteristic size of your system A, B, and C, for example, we consider a box which has sizes of A, B, and C. So if these A, B, and C are somewhat larger than lambda, then we can consider that inside that box we can have some local temperature, and we can have local Maxwell distribution, because these collisions allow that Maxwell distribution to establish to begin with. But if you consider the system, thermodynamic system, at the distance scales, which is less than that lambda, then we can no longer describe this by temperature, actually. So it's no longer a thermodynamic system. It needs some other approaches to treat it. But as you see, actually, this distance is quite small at standard conditions, and then that means that usually when we consider some gases in vessels in your laboratory, then you can use thermodynamic description. There is only one exception to that, and that is called vacuum. Okay, I'm going to introduce vacuum here because this would be the main topic of the next lecture, so I'm going to give a brief introduction to this. So vacuum is, well, ideally a vacuum is when you have no other particles in your volume. So that means a vacuum is when there are no molecules at all in your volume. Of course, this ideal vacuum is cannot be reached. So what's actually important is whether the mean free path of your molecules, how it compares to the average size scale of your cylinder or vessel or another system. So if, for example, lambda is approximately equal to the size scale of the system, this is considered physical vacuum. And that's very important because the physics or the behavior of gas changes drastically as you decrease the number density to such a point that lambda becomes equal to this L. As you see from previous formulas, lambda is proportional, inversely proportional to the number density. So as you decrease the number density, lambda increases. And as lambda reaches the distance scale, for example, of this room, then there would be no collisions happening in the volume of the room, and that means that it would be very difficult for Maxwell distribution to establish. So the only source of thermalization or this establishment of Maxwell distribution would be collisions with walls only. Okay, well, at the same time, actually, the physical vacuum is not the only kind of vacuum you want, because in terms of engineering, they call vacuum any kind of the state of the system in which the pressure of the gas somewhere is much lower than the atmospheric pressure. This is called technical vacuum. Technical vacuum. To engineers, it's important to how you can reach these conditions. If you have the pressure which is much less than the atmospheric pressure, independently of the size of the system, even if lambda is much lower than L, then you will need some technical measures in order to keep this, because the environment is constructed in such a way that it wants for the pressure everywhere to be equal. So that's why if you want to keep this unnatural condition, that pressure of gas somewhere in some vessel, in some system, is much less than atmospheric pressure, then you need to do some work. So you need to add some pumps, you need to get some fittings between tubes and your vessels, which do not allow for the external air to penetrate into your system, to separate it completely from the environment. And that's very difficult. That's why it is called technical vacuum. And actually, physical vacuum can happen even so this is the difference. It depends. Physical vacuum conditions pretty much depend on the size scale of the system. So, for example, this physical vacuum can be established even at atmospheric pressure. If you get this size scale of the system down to 100 nanometer, then you would have a physical vacuum. So in our case, it can happen, for example, if you have some kind of a porous substance here, and these pores, they form some channels in some solid separator in between these two volumes, and when this channel size gets down to 100 nanometers, then molecules inside these channels in our porous substance behave as if they are in vacuum. So that's also can happen. Okay, so that's the remark about the vacuum. What we need to do next, so we have already introduced collisional cross-section, mean free path, average time between collisions, the rate of collisions per unit volume. Next, we are going to delve slightly more into the subject of the distribution of free path. So that would be a free path distribution. As I have said at the very beginning of this lecture, the distance traveled between collisions is the random value, and it changes from time to time. Of course, for the random value, which now it's continuous random value, free path in between two subsequent collisions. So for this random value, of course, we need a distribution. So we need to establish how this value, we need to get some function rho of z, which gives you a probability p, or actually dp, to have a collision when the molecule has traveled somewhere between z and z plus dz. Okay, that's how we're going to do this. Let's consider a single molecule moving. And we know that the mean free path is lambda. But if I assume that this molecule has traveled a very small distance of dz, So it's not like we get a very small distance, not the lambda, but a very small distance of dz. What's the probability for this molecule to experience a collision? The probability is that that's the probability for another molecule center to appear inside a very small element of volume, which is given by the multiplication of the collisional cross-section by this dz. So the probability for the other molecule center to be inside this sigma dz. Okay, that would be something like dp collision. That would be sigma dz multiplied by n. It would be sigma dz multiplied by n. So as you see, actually, this probability is quite small as long as dz approaches 0. Okay. That's the first fact we are going to use. The second fact that we are going to introduce a new function p of z. The probability to travel z without collisions. Probability to travel distance z without any collisions. And now we are going to establish some rules for this. Like, for example, if I want to determine p of z plus dz, so the probability to travel a distance z plus dz, for that we need actually, first of all, we need for the molecule to travel a distance z without collision. Indeed. And also, we need for the molecule not to collide over a distance dz. So not only you need to travel the distance z, but we also need for the molecule not to collide over a distance dz. So since the probability of the collision is given by this, then the probability of not colliding over that distance is given as 1 minus sigma dz times n. So as you see, p of z plus dz equals to p of z times 1 minus sigma dz n. So I can actually write that dp, which is p of z plus dz minus p of z, dp of z equals to minus p of z times sigma n dz. And now we have again an equation, a differential equation, which can be solved by the variable separation method. And that gives us, after I solve it, I get dp of z over p of z equal to minus sigma n dz. And after integrated, from here I get logarithm of p. From here I will get sigma n dz. And the final answer would be that p of z equals to the exponent to the minus sigma n z. So the probability to travel the distance z without any collisions is given by this. During this derivation, of course, when I have a differential equation, if I want to get an answer, I also need some initial conditions. And the initial condition for this equation is that if z equals to 0, then the probability to not experience a collision over the distance 0 is actually equal to 1. Because if you haven't traveled anything, then it's almost impossible for you to get a collision there. So using this, we get this. And now we continue with the determination of the distribution of free paths. So previously we have determined probability to travel some distance without having any collisions. But what we now need to do is to determine the probability for collision to happen between z and z plus dz. This is actually the meaning of the function we want to find for the probability distribution of free paths, because if the collision happens in between z and z plus dz, that means for that particular molecule, the free path is in between z and z plus dz. And how we can determine that? So that probability dp, well, that requires, at first, if this collision happens in between z and z plus dz, that means, first of all, that there were no collisions over the path z. So the probability of that is equal to p of z, while all of the molecules which don't have any collisions over the path of z plus dz, they should be subtracted. So if I have the probability to have no collisions over z and subtract the probability to have no collisions at z plus dz, that would give me exactly the probability to have collisions in between these two. And, well, that's actually approximately equals to dp of z over dz times dz. So to get this density function, I just need to calculate the derivative of the function p of z, and that is actually minus z minus so that would be a minus derivative, actually, minus derivative times dz, because we subtract the function at the larger argument from the function at lower argument. So that's why I need to add minus here. And when I calculate this derivative, using chain's rule, I get the same exponent. But also, moreover, I get this additional factor of minus sigma n. So minus times minus sigma n multiplied by exponent of minus sigma n z. And again multiplied by dz. So that's the element of probability. And next we are going to use the expression for sigma. Well, in here I again assume that the molecules are at rest, and so I need to add an additional factor of square root of 2. So after I do all of these corrections, I would get the equation that dp equals to 1 over lambda multiplied by exponent minus z over lambda times dz. And this function rho of z gives the probability density of a certain free path. And, well, now we can go backwards, and then we can calculate mean free path using. So as we know the probability distribution for the free path, then we can calculate the mean free path using this probability distribution. So we need just to check whether the mean free path would be exactly equal to that lambda which we have used from the very beginning. So let's check it. The mean free path is average z, and by definition it's integral from 0 to infinity of z multiplied by that probability z over lambda exp minus z over lambda times dz Okay, actually we can take lambda out of here and switch to a new variable, which is that over lambda. And now we can integrate that using the integration by parts. So we know how to we don't know yet how to calculate the whole integral, but we can integrate the part of it which is exponent of minus z over lambda. As the rule says, we can integrate this and then we can differentiate this and then we get some result. But of course we need also to have this factor here, lambda times z over lambda times integral of that. Integral is equal to, when we calculate integral, then the factor would be minus lambda times the exponent of minus z over lambda. And this should be calculated in between 0 and infinity, according to this rule. And I can immediately see that when I go to 0, this one dominates. While when we go to infinity, then we have an exponent which dominates the high z behavior, and again it gives us 0. So actually, this first term is exactly equal to 0, and I need to subtract something else. Actually, that is the integral from 0 to infinity of exponent minus z over lambda d z over lambda. And I need also to switch the sign here to plus. So a brief explanation of what's going on here. When I integrate this, I have an additional factor of minus lambda. So I had minus something, so I have an additional factor of minus lambda, and which happens to be, well, I think lambda should be here. This additional factor of minus, when I integrate this over this value, then I have just an additional factor of minus 1. So that minus 1 factor and that minus factor gives you just plus. And then when I calculate derivative of this with respect to z over lambda, that would give me just 1. So altogether that gives me a simple exponent integral. And if I calculate this exponent integral, it's equal to 1. So in the end, I get that the average or distance traveled in between two collisions is indeed equal to lambda, mean free path, which we have introduced at the very beginning of our lecture. Okay, so that concludes the part about the collisions. Next, we are going to consider the transport phenomena. To begin with, actually, the description of these collisions between molecules might sound like an interesting problem, but there is an issue that these microscopic parameters are almost inaccessible in experiments. So if you want to measure something related to microscopy, then it's very difficult. What we actually aim to describe in terms of molecular physics or statistical physics is that we want to give some predictions about the macroscopic properties of the systems, starting from their microscopic behavior. So previously in our statistical physics part of, we have determined thermodynamic parameters of the system from the microscopic interaction parameters. In here, as I have said, these molecular collisions are very important in the process of relaxation. That is the process of going to the equilibrium. And one of the relaxation phenomena is this establishment of Maxwell distribution of velocities. Well, again, that's important, but nonetheless, it's difficult to measure velocities of molecules. But we have some phenomena which are out of equilibrium, they have macroscopic nature. Well, for example, let's assume that we have some gas and we also have administer some other gas, like this is gas 1, but we also add another gas probably from here, the gas number 2, and we create the gradient of the concentration of the other gas molecules. So let's say there are almost no other molecules here, but there are some on this side of the vessel. And of course, it's an out of equilibrium condition of the system, because in the equilibrium, the concentration of these molecules, according to Boltzmann distribution, would be equal. If you don't have any external potential applied, then in the Boltzmann distribution, U is the constant. That means that the concentration of molecules everywhere would be the same. So that means that something needs to happen in order for this equilibrium to be established, and that is called diffusion. That's diffusion. So in here, the diffusion is a chaotic, or I can say that collision enabled which means that the process which is enabled by collisions between molecules, chaotic and collision enabled transport of molecules. So that's the diffusion. The diffusion should be distinguished from the other type of transport, which is called drift, or the ordered transport, in which these kinds of molecules experience some external force, and under the external force, they establish some kind of a common component of the velocity, which is common to everyone. So in addition to the chaotic thermal motion, there will be some common component, which is called drift velocity. So the diffusion is different, not equal to drift. The motion of molecules under the action of external force in the environment. In here, the diffusion, so the molecules propagate from this side of the vessel to this side of the vessel chaotically due to experiencing collisions with other molecules in the vessel. Okay, that's the first transport process we are going to consider. Okay, of course we can consider other transport processes, which one of them is the transport of momentum or viscosity. We have introduced viscosity in our lecture related to the basics of air and hydrodynamics. The viscosity means, I would give a short reminder, that if you have a flow of molecules, so that's of course drift type of motion, flow of molecules in which all of the molecules have some kind of a macroscopic velocity, so you have some flow, and if the speed of this, or if the velocity of this flow is different over different layers, so let's say we have a velocity gradient here, then there would be some shear tension on the separation between these layers, shear stress. There would be some shear stress or internal friction in the gas or in the liquid. So that's the viscosity. The origin of this viscosity is that, well, these molecules which have some macroscopic velocity, they still engage also in the thermal motion. And due to the thermal motion, chaotic motion, some molecules from the high speed part of the gas travel to the lower speed part of the gas and transfer their momentum there. So they experience collision there, and their speed reduces somewhat. So what happens actually that in between these two layers we have the transport of momentum. Transport of mechanical momentum. And when the momentum changes in this layer, in this layer, or in this layer, then also there would be some force associated with the rate of change of the momentum. So that's why that produces a viscosity. And the third transport phenomenon we are going to consider is related to the transport of energy. And as you may probably guess, that's related to this thermal conductivity. Thermal conductivity, or heat conduction. So what happens is that if you have different temperatures in different parts of the vessel, then over time this temperature would become equal in both of these parts. And the reason for that is that molecules in here, they have slightly higher energy than molecules in this part of the vessel. So as they chaotically travel from this side to this side, they also transfer some energy from the hotter part to the cooler part. And due to this transfer, the temperature here, or the energy allocated in this part of the vessel, would increase, while the energy allocated here would decrease. So overall, that would go towards the thermal equilibrium, in which the temperature throughout the whole vessel would become constant. So this is transport of energy. And during the previous studies of this phenomena, which were purely macroscopic experiments, the laws of this phenomena were established. And the first law is related to the diffusion, which is called Fick's law of diffusion. So it says that the transport rate of molecules per unit of time, per unit of some area, is equal to minus the so-called diffusion coefficient. And if I write this in one dimension, then I would write just the gradient of the concentration as the partial derivative of the concentration of the molecules of type 2 over this z coordinate. So let's say that we have this z coordinate here, and in here we have larger concentration of the second time molecule, and here we have lower concentration. And the minus sign says that if I have some area here, then molecules would cross this area from larger that to lower that. So that means that the flow of molecules is directed in the opposite direction to the z-axis. So as you see, that leads to this minus sign. So it just says that actually the flow of the molecules is proportional to the derivative of the concentration over the z coordinate. Similar happens for the viscosity. Well, for viscosity, we know that shear stress tau is equal to some eta, the viscosity coefficient, multiplied by the derivative of the velocity, again over z. In here, I say once again that this velocity is the macroscopic velocity, the velocity associated with drift, the common velocity for all of the molecules inside that part of the vessel. So again, as you see, something very similar. Some derivative multiplied by the coefficient. And in the case of the heat conduction, then we have the Fourier law. law of thermal conductivity, or heat conduction, thermal conductivity. It says that the amount of heat transferred per some cross-sectional area per unit of time is equal to minus kappa, which is called thermal conductivity coefficient, multiplied by the partial derivative of temperature with respect to z in a one-dimensional case. Of course, this can be extended to multi-dimensional case, but I'm going just to start with the one-dimensional case and then go to multiple dimensions. So once again, I would like to write the definitions. D is the diffusion coefficient, while kappa is thermal conductivity coefficient. The coefficient eta is called viscosity coefficient or also dynamic viscosity. Those are synonyms. Dynamic viscosity. So what we aim to do in this part of the lecture is we want to determine the relationship between these coefficients related to this transport phenomena and microscopic properties of the gas, like mean free path, collisional cross-section, and so on and so forth. So since all of these phenomena, they have generally similar nature, we are going to start by describing a transport phenomenon of a general kind. So let's assume that we want to consider transfer of or transport of some macroscopic property x, like for example energy, momentum, or actually the number of particles. And we assume that a single particle, a molecule, single molecule carries small x of this. So the macroscopic quantity capital X can be determined by summation of small x, and when they add up, they would give us a capital X. Well, I guess you can even say that, for example, for the diffusion, then x equals to 1. So a single molecule just carries itself. So if you consider that the transport of the number of molecules, that means the number of molecules per single molecule is 1. If we talk about the viscosity, then each molecule carries some momentum, which is equal to the product of the mass of the molecule multiplied by the macroscopic velocity v of that molecule. And if I talk about thermal conductivity, that means that each molecule carries some energy. And since we consider a gas, that mostly that energy is the of the kinetic nature, and it is equal actually to the molar heat capacity at constant volume divided by capital R, universal gas constant, multiplied by kBT. Of course, by energy, I mean not only the energy of the translational motion, but also energies of rotational motion, if there are any, or vibrational motion, if there are these types of motion for a molecule. And if I don't want to bother with actually how these molecules are constructed, whether they are single atomic or diatomic or triatomic, then I just write CV over R to represent the amount of energy related to a single molecule. Okay, so that means that actually all of these processes can be described using the very same approach. what we are going to do next is that we have this z-axis over which we see how these physical quantities are being carried, and as we know, these quantities are being transferred from one side to another by molecules moving in these both directions. And as we know, actually, the molecules move without any collisions approximately for a distance lambda. So that means that the molecules which cross this cross-section from this side, they start from, okay, let's say this is a 0 coordinate. So they start from minus lambda. So they are located in between this area and another area which is separated from this plane by the distance lambda. The same happens for the other side. So the molecules which go from this side to here, they start their motion somewhere in between 0 and lambda here. So that means that the amount of x being transferred per unit of time per unit of this cross-sectional area can be determined as follows. That we need first of all to write 1 over cross-sectional area multiplied by dn, so the number of molecules transferred in the right direction per unit of time, multiplied by x carried by each of these molecules. And of course, since the conditions to the left and to the right can be different, then actually potentially this x can be different. As you see, if it contains temperature or it contains velocity, then of course that x would be slightly different for different special coordinates. And I need also to subtract the flow which goes in the other direction, which is given by this dn to the left over dt times x carried from the left side. Okay, that is it. Now we are going to determine this dn over dt. Well, actually, we have determined that previously, but in here we are going to use a very crude mathematical approach, which is not strict in any way, but for some reason it gives a result which is even coincides with the coefficient with the correct one. So it gives even the correct coefficient, not only the order of magnitude or the general formula, but also the coefficient is correct. Well, when it comes to diffusion, actually. So in here, we are going to assume that molecules, they cannot move in any arbitrary direction. They can move just in the directions parallel to the Cartesian axis in our problem. So they can go upwards, downwards, leftwards, rightwards, and also in these two directions. And as you see here, for the fraction of molecules moving to the right is actually within this very simplified, overly simplified, and actually wrong picture. But within this picture, it's 1 over 6 of the total molecules. So the number density of the molecules moving to the right is 1 over 6 multiplied by n. And if I want to determine the number of molecules crossing, I also need to multiply that by the average thermal speed of these molecules. Thermal speed, not the macroscopic speed, but thermal speed. So this is the number. And as you see here, actually, if I insert this number into this expression, what I would finally get is the following. It's again overly simplified treatment of these processes, because the mathematically rigorous treatment would be much more elaborate and it would take much more space for me to derive it. That's why I give you some kind of a simplified picture, which is nevertheless leads to the correct result. So in here, if I insert, then I can write that dx over dt is approximately equal to okay, A, 1 over, oh, well, let's say I have also A here, per unit of area. So that would give me 1 over 6 multiplied by concentration of molecules moving rightwards, multiplied by the average thermal speeds of molecules moving to the right. And of course, you might understand that if the temperature is different, then this mean speed would be different too. And also multiplied by x carried by each of these molecules. And then I subtract 1 over 6 and moving to the left, v moving to the left, and x of molecules moving to the left. And since these molecules start at different points of space, I can just say that I deal with the same function. Let's say some function f, which is dependent on the special coordinate. And in here, this function corresponds to f of minus lambda, while in here, this is function f of lambda. So I need to subtract f of minus lambda minus f of lambda, and assuming that my lambda is very small, so that all of the macroscopic properties of the system change only very slightly, then I can write that this is actually equal to 2 lambda multiplied by the partial derivative of f over z. Partial derivative of f over z. Okay, so as you see, this is where I get this derivative, partial derivative of something over z. So now I'm going to replace f by these quantities. So I'm going to write that this is actually equal to 1 over 3, because I had 1 over 6 as in my f, and that's constant. I can take that out of the derivative. So then I need to multiply this by lambda. And now I have the partial derivative of concentration times thermal speed times x over z. Okay. Now let's apply this equation to all of these transport phenomena. Let's start with diffusion. Diffusion. In the diffusion, we know that x exactly equals to 1. So actually, this is the constant which can be taken out from the derivative. In the diffusion, we also know that temperature throughout the system remains constant. So mean speed is also constant and can be taken out from the derivative. So once I do all of that, I get that dN over A dt, where n is actually my capital X, is equal, the flow of the molecules equals to minus, okay, I also have minus here because again, I subtract the function with larger argument from the function with lower argument. So if I have minus in addition to this derivative, and get me minus lambda over 3 multiplied by average v, and what remains in this derivative is the gradient of the concentration of these molecules, dN over dz. And looking at this equation, and comparing it with fixed law of diffusion here, I get that the diffusion coefficient equals exactly lambda times mean speed over 3. And that is an equation which can be obtained also in rigorous calculations, which include that all of the molecules travel different paths between collisions, and they have different velocity components. They can be directed arbitrarily, but after you get all of this complicated stuff together, you would get exactly the same answer. That's why I happen to use this approximate approach here. Well, the predictive capability of this approach for thermal conductivity and viscosity is slightly less, but nonetheless it gives the answer in the correct order of magnitude. So what we are going to do is now apply this to the viscosity. In the viscosity, we assume that temperature is constant, but, well, small x is mass of the molecule multiplied by the drift velocity of that molecule, the macroscopic velocity at that point of space. And secondly, well, the concentration is constant. The number density everywhere is constant. That means that if I plug everything here, then I can take all of the constant values from that, and that would mean that the momentum per unit area per unit of time transferred through that plane, which separates different parts of my gas, equals to minus lambda over 3 multiplied by n multiplied by average V multiplied by mass of a single molecule, and again by the derivative of dV over dz, where V is the macroscopic velocity. Now I look closely, somewhat more closely here, and I see that the product of the number density by the mass of the single molecule actually give us the density. So this is minus lambda over 3 multiplied by density multiplied by mean thermal speed times partial derivative of V over Z. And looking at this, comparing it with the viscosity equations, I get that the viscosity coefficient eta is equal to 1 over 3 times lambda times density times average mean speed. Well, the final phenomenon which remains for us to study is thermal conductivity. So this is thermal conductivity. Well, in here, well, temperature is not constant. So that means that number density is not constant. The pressure is constant. And also, mean thermal speed is not constant. So that's really something very, it seems like something very difficult here going on. Finally, the small x is equal to CV over R times KBT, the energy per single molecule. Well, so if I plug that of everything is here, it seems like I can take nothing out of my derivative, but that's actually wrong. During thermal conductivity, we assume that the concentration distribution remains in its steady state, so it doesn't change with time. So that means that the number of molecules going in one direction per unit of time equals to the number of molecules moving in the other direction per unit of time. And that is what allows us to resolve the difficulty, because this number of molecules are equal to n to the right, V average to the right over 6 equals to n to the left, V average to the left over 6. So that means that while n and thermal speed are not constants, their product remains constant. Otherwise, it wouldn't be impossible to have, first of all, constant pressure, and secondly, to have a balanced flow of molecules from one side to another. And since we have this balance, we can actually take out the product of n times average V, or mean speed, from the derivative, and that really helps. It allows us to go around the problem. So the amount of heat transferred by molecules due to the thermal motion is equal to 1/3 multiplied by lambda multiplied by n times mean speed. So it doesn't matter where I measure it. And multiplied by the derivative of x. Well, in x there are also lots of constants. I can take them out. This is Cv over r multiplied by Kb. And then goes the derivative of temperature over z. And also, of course, the minus sign here. So all of this, which is, according to this equation, equals to 1/3 multiplied by lambda and mean speed Cv over r times Kb. Well, now that doesn't look like a very beautiful equation, but it can be made better. It can be made better. Well, as you see, the ratio of Kb over r actually equals to the Avogadro number. So I can go like this. Now I have n over an Avogadro number. So what I'm going to do here is actually the following. I'm going to multiply n by mass. So that add the mass of a single molecule and add the mass of a single molecule in the denominator here. So altogether, these two would give me the molecular weight, while these two would give me the density. So finally, I would get 1/3 multiplied by lambda times density times mean thermal speed multiplied by Cv over mu. And that looks kind of good, because if I divide molar heat capacity at constant volume by the molar weight of the substance, what I get is actually the specific heat. Specific heat at constant volume. So in here I have small letter Cv. This is actually a specific heat capacity at constant volume, or specific heat at constant volume. And that's for kappa, thermal conductivity coefficient. And of course, these three equations for the transport coefficients, they should be remembered. So I'm going to write them again here. That d is 1/3 times lambda times mean speed, while the viscosity is 1/3 times lambda multiplied by the density multiplied again by mean speed. And for thermal conductivity, I have 1/3 times lambda rho average V multiplied by the specific heat at constant volume. Actually, these equations can be determined from some simple considerations like the dimension analysis. For the diffusion coefficient, actually it has the dimension of meters squared over second. Eta has the dimensions of Pascal multiplied by second, and the thermal conductivity has the dimension of let me see, that is the heat flow is joule per second per meter squared. It should be multiple of thermal conductivity by the temperature gradient. The temperature gradient is Kelvin over meter, so the meter can be eliminated from here. So what remains is that kappa equals to joule per Kelvin multiplied by okay, over meter over second. Okay, joule per second is watt. So this is watt over meter over Kelvin. So that's the unit for the SI unit for thermal conductivity. And if you look at this, actually this velocity is responsible for giving this reciprocal seconds. The specific heat is responsible for having joule per kilogram per Kelvin. Now we have the uncompensated kilogram, but to compensate for kilograms in the denominator, we need also to add this density, which is kilogram per meter cubed. And then I also need to add lambda, which is the dimension of meters, in order to set up the correct exponent for meters. So these equations up to this coefficient of 1/3, which can be remembered, can be determined just from the dimension analysis. And also this one is more or less strict, while this one and this one, well, they're actually fairly approximate. Okay, so the next part that we have established this formula, so I'm going to look at how these coefficients change as I change the conditions of the system. So let's say I keep my system at a constant temperature, but change, for example, its density. What would change with these coefficients? That's very important. So let's start with the diffusion coefficient. D equals 1/3 lambda times mean speed. Okay, as I keep my temperature constant, that means that this one will remain constant. But lambda is equal to 1/√2 times sigma times the number density. Sigma is the property of molecules of which my gas is constituted. So this changes with pressure. So that means that lambda is inversely proportional to pressure. And that means that the diffusion coefficient is inversely proportional to pressure too. Good. Now we get to the viscosity coefficient. If we compare the equations for the viscosity coefficient and the diffusion, you will see that actually I can write that the viscosity coefficient is the product of the diffusion times the density. The diffusion coefficient is inversely proportional to pressure, while the density goes the other way. The density is equal to n times m, where n is the number density. And as we know that pressure equals to n kBT, so that means that actually the density is directly proportional to pressure. But if you calculate this product of the density and the diffusion coefficient, that would give us actually a constant. So eta remains constant as we change the pressure. And now we go to the thermal conductivity kappa. We look at the difference between equations for thermal conductivity and the viscosity, and we see that the only difference is this CV. The specific heat, at constant volume. So I can write that this is eta times CV. Well, CV is the property of the gas which is independent of its concentration. That's why actually this is once again is the function independent of pressure. But what will happen if I change temperature while keeping, for example, pressure constant? If I change temperature while keeping pressure constant. So in here, well, it becomes slightly more complicated. Let's say we keep the number density constant. The number density constant. Then lambda would remain the same while the V would change. And as we know, average speed is proportional to square root of T. For the diffusion, Okay, in here I keep number density constant. That means the density doesn't change. Again, proportional to the square root of t. And for the third one, I need to multiply by CV, which is again the function which is approximately independent of temperature, and I get that the thermoconductivity coefficient is again proportional to square root of t. But that is assuming that number density is constant. What would happen if the pressure is constant? And that means that as I increase the temperature, my number density, so as we know, pressure is N times Kb times T. So if I increase temperature, I need to decrease number density in a proportional factor. So that means that number density is inversely proportional to T. So once I get here, I get that lambda becomes inversely proportional to t, while v is directly proportional to square root of t. So in here, d becomes proportional to square root of t over t. So that is t to the minus 1 over 2. And this is for the diffusion coefficient. Next, we go to the viscosity. In the viscosity, we multiply diffusion coefficient by the density, and the density is equal to, as we know, okay, this is actually n times m. So the density is again inversely proportional to temperature. So I add another function which is inversely proportional to temperature, and that means that my viscosity becomes proportional to t minus 3 over 2. And now we get finally to the thermal conductivity. And well, as we know, usually thermal conductivity behaves in the very same manner as the viscosity, because they are just different by specific heat at constant volume. So now I get for the thermal conductivity that it's proportional again to t minus 3 over 2. So that's depending on what we keep in constant and what we do not. So in here the pressure is constant, temperature is not. In here the number density is constant, the temperature is not. While previously, initially, I have considered that the temperature is constant while pressure is not. So in here, temperature is constant. It's a wholly remarkable law that actually viscosity and thermal conductivity do not change as you change your pressure. And it was really established and confirmed experimentally. Of course, that's valid up until your gas in the vessel is not in a vacuum state. As I have said, vacuum is when the mean free path becomes approximately equal to the size of the vessel. And now we get into the final part of the lecture. We are now going to consider the diffusion. Well, probably not. We are going to consider two subjects here. The first one is the equations which describe the diffusion and heat conductivity. So one of these equations is called heat equation. So let's assume that we know how initially the temperature has been distributed in our system. We know the distribution temperature T of Z. And we know actually that due to the, if the temperature is not constant, there would be some flow of energy from one part of the system to another one. What we aim to determine here is actually how the temperature would change with time. So let's consider a small portion of some substance. It doesn't necessarily need to be a gas, because heat conductivity happens quite similarly also in solids and in liquids. So we are now considering the very general case. So let's say we have here z, we have here z plus dz, and we know that in here the flow of heat, which is dq over the cross-sectional area over dt, is equal to minus kappa multiplied by dt over dz. But of course, that should be determined at the point z. So all of this calculated at z. When we go here, there is also transfer of heat through this plane. And in here, that's everything remains very the same, but it should be calculated. So both the thermal conductivity coefficient and the temperature gradient should be calculated at z plus dz. Of course, these two flows are not necessarily balanced. So if the gradients are different, or if thermal conductivity in here and here are also different, for example, we have different materials, then what actually happens that some energy is being accumulated here. And as the energy is accumulated in that part, that would lead to the temperature increase. So I can write that, let's say, product of the density multiplied by the specific heat multiplied by temperature. So that's the amount of energy which is stored in this part of my system. And if we calculate the time derivative of this, then it should be equal to the inflow of heat into our system. So that means that I need to calculate it as dq over a dt at point z minus the same function at z plus dz. And again, once my dz is essentially small, then I can write this as a product of the derivative times dz. And of course, I need to get the minus sign here. So that would give me minus multiplied by rho times cv times t, but I also need to multiply that by dz. And here I get minus dz multiplied by minus kappa of z multiplied by the derivative of dt over dz. Okay, and well, this is dz multiplied by the partial derivative of this over z. As you see, I use here the sign of partial derivative because actually in here everything is a function of different variables. It's a multivariable problem. We have the special coordinate z, and also we have a time variable t. So as we have the functions of two variables, I need to use the partial derivative sign if I calculate derivative over time or derivative of the special coordinate. Now this derivation brings me to the final part, so I'm going to derive the heat equation in its final form. So this is d rho cv t over dt equals to kappa multiplied by d over dz multiplied by, well, not kappa is inside, kappa d over dz t. Okay, so that's a heat equation. It describes you the evolution of temperature when you have some special distribution of temperature. So if you have some initial conditions, you can predict how the temperature would change in our system. In a very similar manner, we can determine the diffusion equation. Diffusion equation. It's equation of a very similar type, and repeating all of the same considerations as we have done for the heat equation, we can get the following, that the time derivative of the concentration of molecules, of added molecules, equals to, okay, again, d over dz multiplied by the diffusion coefficient times dn over dz. And as we have established previously, since at a constant temperature diffusion coefficient is independent of the pressure or the number density, I can take out my diffusion coefficient out of here and get that this is equal to d times second derivative of the number density over z. So that's diffusion coefficient. What's interesting about diffusion and heat conductivity, that according to these equations, it happens instantaneously. And the speed of heat conductivity and the speed of diffusion, according to these equations, actually exceeds the speed of light. Let me show this. So let's say that we have this kind of a distribution, for example, for temperature or for the number density of some molecules here. So let's say this diffusion. We have molecules here, we have no molecules here. And if we solve this diffusion equation, then after a very small moment of time dt, the distribution would look like this. The problem here is that within this tail, the small tail actually, well, is non-zero at all coordinates, even for those of them which are, for example, larger than z0 plus speed of light times the amount of time passed from the initial moment. So formally that means that the speed of the diffusion is infinite. Of course, it's not so. And there are two reasons for that. In here, we have number density, some macroscopic quantity which represents you the concentration of molecules somewhere. But actually, you can treat number density as the function which gives you some average, or actually it gives you some probability for the molecule to be found somewhere. And once this concentration becomes very small, as in this tail, very far away from this initial border between these molecules, when we get far away from here, that number density becomes so small that it actually corresponds to not having even a single molecule there. It's an exponentially decaying function, very fast decay of this function. And it reminds me somewhat of homeopathics, in which you dilute some kind of active molecules in water, and you continue to dilute and dilute and dilute it until you have no initial molecules in your solution left. But formally, of course, while you do these procedures, you will have, for example, some finite, yet very small concentration of these molecules according to these laws. but nonetheless, the molecules are discrete particles, so it doesn't mean that if you have some non-zero concentration somewhere, then there would actually be some molecule there. And secondly, there is another limitation to the thermal conductivity or these types of equation. Actually, these types of equations arise from our human nature because it's more convenient for us to deal with some continuous equations which describe some kind of a continuous function in space instead of describing some discrete motion of zillions of particles somewhere which are colliding in some very complicated and chaotic way. So these equations model that chaotic motion and they present it in a convenient continuous form. Nonetheless, that means that some parts of this motion are being neglected. Now, for example, actually, the thermal conductivity as well as diffusion happens due to the multiple collisions. But if you have, for example, the amount of time in which no collisions have happened whatsoever, so for example, dt is much less than lambda over the mean speed of the particles, then no collisions have happened anyway, so what can diffuse there? So this equation becomes wrong on this scale. And moreover, we imply that we use some Maxwell distribution. And if you look at the Maxwell distribution, now let's go and move to the Maxwell distribution. It says that there is this probability that molecules have this velocity v, and inside Maxwell distribution there is no law which prevents from this v to be larger than speed of light, actually, in this equation. It means that we are located within classical physics, but when we go to these extreme velocities, actually they are improbable, first of all, but formally there is some probability, a very small probability, to have this velocity very close to the speed of light. But of course, first of all, we need to use different equation for the kinetic energy, not mv squared over 2. We should use a different one. And secondly, well, again, there would be no such molecules whatsoever because the probability is so low that, again, as in the homeopathics, when you have such a small probability, not even a single molecule would have such a speed. Okay, so that's for the infinite that's for the infinite speed of heat transfer and infinite speed of diffusion. While formally it indeed is infinite, the actual speed is of course limited by the physics you have at hand, and which is not included in our continuous equations. The next thing we are going to do is actually we are going to consider the diffusion as a type of a random walk. So actually, as I have said at the very beginning, that's random walk diffusion. As I said at the very beginning, if we have the larger concentration of molecules here and lower concentration here, then over time, these molecules would travel from here to here. But of course, the distance between this part of the vessel and this part of the vessel usually is much larger than lambda, which is approximately 100 nanometers. So that means that the travel from here to here happens, well, in a chaotic manner. For example, if you look at the molecule starting from here, then when it travels, it goes over the multiple collisions, and, well, it moves chaotically in all directions, but at some points of time, some of these molecules happen to travel to the second part of the cylinder, of the vessel. So we need to establish some law which allows it to describe how far the molecule moves as it goes through these multiple collisions. in here, I'm going to introduce the model of a random walk. I'm going to simplify the process. I'm going, first of all, to assume that over each collision, the molecule travels exactly by the distance lambda, which, as you know, is not true, but for our purposes, this is enough, because we don't want to consider more complicated case when this lambda can be different. Secondly, we are going to assume that the time between collisions is also fixed. So I'm going to say that over time tau, exactly one collision happens. So this molecule moves over time tau by this distance lambda, and so we can consider its motion as the sequence of steps. So we start from the initial location of molecule, which we denote R0. And at the next step, how we determine the position of the molecule? We add a random vector lambda. We know the length of this vector, the absolute value of this vector, but we don't know the direction, because the direction is has equal probability in all directions, actually. On the next step, we again add the random vector lambda. So how we are going to describe the motion? If we, for example, try to average this equation, so of course, in each case, this sequence of R1, R2, and R3, if you consider multiple experiments with molecules starting at the very same point of space and moving forwards using multiple collisions with other molecules, then these vectors R1 and R2 and so on and so forth, they are fully random. And what we can do is we can determine like some of the averages. If we try to determine the average of each vector, let's say we calculate average of Ri, then according to this equation, this average should be equal to average of Ri minus 1. So the average of this vector on the previous step plus the average of the random vector lambda. And since average, this vector lambda can be directed in every direction with the equal probability, then this average equals to 0. So that means that over time, actually, the average of this vector remains the same. So as if it says that the position of the molecule would not change, because the average of this vector would be the same as the initial position. That's not so true, that while the average remains the same, but the deviation from that average changes over time. And as we know from our previous lectures, when we describe random variables, what's important is not only to know its average, but also to know its variance, or mean square deviation. So now we are going to look at the squared vectors. So let's say R1 squared is actually equal to, if we squared up all of this equation, and we get R0 squared plus 2 multiplied by the scalar product of R0 times random vector lambda plus random vector lambda squared. And this means that if I, for example, try to take average of this, that would give me that average of R1 squared is exactly equal to R0 squared plus, well, this gives 0, because lambda can be directed anywhere, and but this one gives lambda squared. So altogether I get that at the step number n, Rn squared should be equal to R0 squared plus n times lambda squared. Or that would say me that, but if I subtract from this one, that would say me that the root mean square deviation would be exactly equal to square root of n, the number of steps, multiplied by lambda squared. So this is lambda times square root of n. And this is one of the main laws which describe random walks, and they also describe the diffusion. That actually this n is proportional to the amount of time passed from the very beginning. So this law says that the average, okay, let's say root mean square distance from the initial point for the particle which undergoes the diffusion, the random motion, is proportional to the square root of t. And as you see, it's very much different from the law which describes the macroscopic motion or drift motion. In the case of drift motion, if you have some kind of a common velocity for all of the particles, then of course the displacement of the particle would be proportional to the linear time, directly proportional to the time, not the square root of time, but time. So this square root of t arises due to the randomness in the scattering process. So you not go into some direction in particular, you go in all directions at the same time. But as you go over these random motions, you get displaced farther and farther away from the initial point. But the displacement increases proportionally to the square root of time, not the linear time. Okay, in the case of the diffusion, if you look at the diffusion equation, I'm going to write it once again, that dn over dt equals to a diffusion coefficient times this kind of a derivative. If you insert as the initial condition the following distribution, the Gaussian distribution for these molecules, for the number density, something like some constant coefficient over sigma multiplied by exponent of minus x average squared over 2 times sigma squared. Then as you allow this distribution to propagate over time, then actually the solution at this is a solution at the initial moment of time, the distribution of the number density, but the number density at the time t would be equal to a, would be the same. It would be the same Gaussian distribution, but this deviation would be slightly different. In here, actually, a sigma of t squared will be equal to sigma 0 squared. So let's say this is sigma 0 plus 2 times d times t. And once again, as you see, as you go over time with this diffusion, this parameter sigma, which allows it to describe root mean square deviation of the molecules from this center of the bell, increases linearly with time, but this is a squared. But if you look at the root mean square deviation, the increase would be proportional to the square root of t. So that actually again means that inside the diffusion equation we have this physics related to multiple collisions incorporated in it. And if you look at that physics from a different point of view, from microscopic points of view, we see that the displacement of the particle is proportional to square root of t, and the same actually is given by the diffusion equation itself. So the microscopic approach to this problem yield the very same result. We have a few zero-level problems, but essentially those are related to direct application of the equations I have derived during today's lecture. So in problems 26, 27, and 28, what you actually need to do is to use the following equation for the mean free path, 1 over square root of 2 times the number density times sigma, where sigma is pi times the diameter of the molecule squared. So if you are asked to find the diameter of the molecule, you can get it from here. And also you may probably have a diffusion coefficient, thermal conductivity, viscosity. So once again, the diffusion coefficient is 1 over 3 times lambda times mean thermal speed of molecules. If you have forgotten, for example, how mean thermal speed of molecules can be determined, that should be taken from the lecture about Maxwell distribution. That's equal to 8 kBT over pi times the mass of a single molecule. And as I have said previously, it's much more convenient to use this in the form of 8 RT over pi mu, where mu is a molar mass, R is a universal gas constant, as usual. The next one is for the viscosity, which is 1 over 3 times lambda rho mean thermal speed. And the next one is for thermal conductivity is 1 over 3 times lambda rho V times now actually CV, specific heat at constant volume. So let me see if there is anything non-trivial in these zero-level problems. If there is, 28, 29, 30. So actually, these are zero-level problems for today's seminar. Or not. Viscosity, thermal conductivity, nitrogen. Okay, let me see. The problem 28. You need to calculate thermal conductivity from the viscosity. Well, thermal conductivity is here, viscosity is here, and as we see, thermal conductivity is viscosity times CV, where CV is specific heat. So if you actually calculate that for gas, it's probably more convenient to use this. This molar heat capacity at constant volume over the molar mass of this nitrogen or whatever. Okay, next is the diameter. Well, once again, once you have the viscosity and you also know the conditions, room temperature and atmospheric pressure, so that allows you to determine this and this. So that means that you can determine mean free path of molecules. And from mean free path, and also you know the number density of molecules, you can determine sigma. From sigma, you determine the diameter. That's fairly straightforward, in my opinion. That's about problem 28. The problem 29. Estimate the amount of heat per 1 meter squared lost by a room per unit of time through a single chamber double glazed window. So it's a usual technology applied in many countries when you want to have a glass window. If you just make your window out of a single block of glass, then the thermal conductivity of that window would be quite large. So in order to reduce the thermal conductivity, in order to keep the room warmer or thermally isolated from the street, what you actually need to do is that use the fact that actually the thermal conductivity of gas is quite low. If you compare thermal conductivity of gas to thermal conductivities of solid or liquids, generally it turns out that thermal conductivity of gas is really small compared to other one. The reason for that is actually that the number of molecules in gas per unit of volume is very small. So the amount of energy they can carry out, oh, well, that's the wrong explanation usually. Because as we have established during our lecture, thermal conductivity of gas is independent of the number of density. Interesting. But nonetheless, thermal conductivity of gas is really small compared to thermal conductivity of liquids and solids. So in order to get less of the thermal conductivity in windows, we have actually two layers of glass which are separated by a layer of air in between them. And we know that kappa is for air 2.3 times 10 to the minus 2. Kappa is 2.3 times 10 to the minus 2 watts per meter per Kelvin. Watts per meter per Kelvin. And well, just to show you how small the conductivity of air is, we can compare it with the thermal conductivity, for example, of copper, of any metal. So copper is the metal, and its thermal conductivity is approximately, I don't remember the exact value, probably something like 3 or 5 of watts per centimeter per Kelvin. Per centimeter. So that means that 300 of watts per meter per Kelvin. If you compare 300 with this one, it means that we have a 4 order of magnitude difference. That's really huge. So this for copper, metallic bodies have really good thermal conductivity. Well, in the case of air, it's really small. And once we want to determine the heat flow, so we know that the distance between the glasses. So this distance is h equal to 33 millimeters. And the temperature difference between the room and the environment is delta T equal to 50 kelvins. 50 kelvins. So in order to determine the heat flow, as we know, we need to calculate the following. The Q, so the amount of heat per unit of time per unit of cross-sectional area is equal to kappa times minus the derivative of temperature over the coordinates. So let's say we have x-axis here. So here is the room, delta T. Here is the environment, so actually temperature, and here you have temperature minus delta T. So as we see, actually this derivative should be negative. And moreover, if we look at the stationary condition of this system, if you look at the stationary condition, then as we know, there is this thermal conductivity equation that, well, we don't even need some thermal conductivity equation here. If we look at the stationary condition, then actually the heat is not being accumulated anywhere. So the amount of heat traveling here through this cross-section is exactly the same as the amount of heat which travels through any other cross-section in between these two windows. So that means that this dt over dx is actually constant. So that means that we have a linear function which describes the distribution of temperatures in between these two windows. And then this derivative dt over dx can be simply calculated as kappa minus delta t over h, where h is the distance between these windows. And in our problem, we don't consider the heat conductivity of glass, because as I have said previously, almost any substance has much larger thermal conductivity than air. So in here, air is actually the thermal insulator. So that allows us to determine finally the answer. So we just put the delta T, kappa, and H. We know all of these values, so we can calculate the results. So again, nothing difficult, except that we need to guess that the distribution of temperature in between these two glasses is actually linear. That is the most non-trivial part of this problem. Okay, the next one. In a narrow tube with nitrogen under normal conditions, there is a stationary process of diffusion of a small admixture of helium. The difference in helium concentration at the ends of the tube is maintained at the constant level, while the particle flux in the tube is given. Estimate the mean free path of helium atoms in nitrogen and their collisional cross-section with nitrogen molecules. We know the average thermal speed of helium atoms. Well, once again, as you see, even from the equation, so we are given some problem which is related to the diffusion. Okay, from the initial from the conditions of this problem, we can determine the diffusion coefficient actually, and we know this average thermal speed that allows us to determine lambda. And then, when we have this lambda, well, we can determine, we also know the concentration or the number density of nitrogen, because mostly this tube is filled with nitrogen. That's why this N should be the number density of the nitrogen. From this we can determine the collisional cross-section. And that's the end. So in all of this, I'm going to just to calculate the diffusion coefficient probably. I think this is the part which is unrelated to these equations directly. So we need to use the conditions of the problem to calculate the diffusion coefficient. So I'm going to draw the tube. So we have here some N helium, while we have on the other end N helium minus delta N. And there is a constant flux of helium molecules from one side of the tube to the other side of the tube. And according to the Fick's law of diffusion, this current this current is actually the number of molecules per unit of time per unit of cross-sectional area is the diffusion coefficient d multiplied by the derivative of the concentration of helium over x, where x which goes this side, and I also need to have a minus sign here. So in here, once again, this derivative is negative, and since this is g is constant throughout everywhere in this tube, we are dealing with a stationary problem, and that means that helium molecules do not accumulate anywhere inside the tube. That means that g as a function of x is constant. So once again, we have a constant derivative of the helium concentration over x. So that implies that actually the dependence of concentration of helium as a function of x is linear as you go through this tube. And that once again means that we can replace this derivative by d multiplied by delta n over the tube length L. So from here you can determine d. So d is G times L over delta N. And then I'm going to repeat all of the stuff which I have said previously. Once you know D and you know thermal speed, you can determine lambda. In this lambda, the only thing which you should care about is what you have as N in that lambda. Lambda is 1 over square root of 2 divided by N of nitrogen times sigma. That's because actually your helium molecules can collide with nitrogen molecules and other helium molecules. But since we have a very small admixture of helium molecules, that means that most collisions happen with nitrogen molecules. And this collisional cross-section is actually the collisional cross-section for the molecules which might have a different size. This is the helium-nitrogen collision cross-section. So that's why actually at the very beginning of the lecture I have determined the collisional cross-section for molecules which have different radii in here. And well, once you determine that, you know also the nitrogen concentration, and then you get to the collisional cross-section which you need to determine in this problem. Okay, then the next one is, okay, I think that's all for zero level problems. We now need to go to the type 1 problems. So in here we have 3 types of problems, but I believe that one of them I have solved previously. I'm going to ask you whether I have solved this problem. First, I'm going to formulate it and ask you if you remember this problem in any way. So it says that the problem is 2.44, and it says that we have a disk and we have another disk separated, well, that's not a good figure, separated by a small distance h. That's a very small distance h between these two disks. Okay, the radius is a, much larger than h, and one of these disks is rotating at the angular velocity omega about this axis, above the common axis of these two disks, while the other disk is stationary. Find the moment of friction forces acting on the stationary disk if the viscosity coefficient of the gas between the disks is equal to eta. Well, I believe I have solved something like this, but I would like to ask you whether you remember that I have solved any problem which looks like this, or if you want me to solve it again, if you've forgotten the solution. Please write in chat. I would see your answers immediately, if anyone is here. Could you review again? Okay, okay. Thank you. So once you rotate something, what we actually want to discuss is that if we consider 2 small areas of this disk, if you look at this from the above, there is one small area of the disk and another small area of the disk which is under this small area. So this is how these disks look above. And as you look at this small area, in the rotating disk, it moves at the velocity of omega times r, where r is the distance from this small area to the center of the disk. And the disk below doesn't move. And we can reduce this problem to a problem of 2 planar surfaces, one of which moves at the velocity v, while the other one moves, well, is at rest, is stationary. And looking back to the problems related to viscosity of liquids, we might know that actually in this motion there is some shear stress induced inside the gas, and this shear stress is equals to viscosity coefficient multiplied by dv over dz, where z is this axis. So, well, of course, in here the linear law of the velocity is established in between these two disks. So I can calculate this as eta multiplied by v over h, where h is the separation distance between these disks. So at the end, I get eta omega r over h. Okay, that's the shear stress, but the shear stress acting on the disk which is below goes in the same direction as the velocity of the disk above. So it goes in this direction, and this shear stress produces the force dF, which is equal to the product of the shear stress by the element of area of which we consider dA. Element of area dA, and that force again produces the momentum, the moment of, okay, there is a moment of force, and the moment of force is the product of force by the distance from the axis about which we calculate the moment of force. So in here I have dF multiplied by r. And since the F and R are perpendicular to each other, then the moment of force is exactly equal to the product of these two, because actually we need to calculate the product between the force and the distance multiplied by sine of the angle between them. And since the angle, we have a right angle in between them, then the sine is equal to 1. So I just have only the product of force by the distance. So the contribution of the area to the total moment of force equals to tau times r times dA. Okay. So once again we replace tau with this one. And as you see, now r is squared here. And now we need to sum up all of the contributions from all of these areas on the disk in order to calculate the total moment of force. So I need to integrate eta omega r squared over h multiplied by dA. Well, and I need to integrate over the whole area of the disk, and I'm going to reduce this integral to the integral over the radius, because as you see, what actually matters is the distance between this area and the axis. So it means that we can combine all of these areas which are located at the very same distance from the axis into a circular ring, and replace this by the area of the ring. So in here I would have the integral from 0 to small a, as we have in the problem. The radius of the disk is small a. So in here from 0 to small a, eta omega r squared over h multiplied by the area of this ring. The area of this ring is equal to pi times dr squared. Of course, I could have written like something like 2 pi r multiplied by dr, and that would not change the answer. But since I have already r squared here, and well, I think it's convenient to have also r squared here. And I also need to separate this integral from our previous calculation from the element of moment. So now I just need to calculate an integral. I take the constants outside of integral and then integrate r squared dr squared. That would give me r to the 4 over 2. So in the end, I have eta omega 8 to the 4 pi over h. I think this is the final answer. Okay, it's also coefficient. So that's the end of the solution. Any questions about this one? Well, see no questions yet, but probably it takes some time to write them. So I'm going to check in a few minutes. Now I'm, without any delay, I'm going to start with the next problem. Why did you change capital A to the small a? I didn't change the capital A to small a. Small a is the radius, capital A is the area of the whole disk. What I actually changed is that I changed integration over the area to the integration over the radius. From dA, I go to the dr. And the way I do this is that I combine all of these small areas which are located at the same distance r from the axis of rotation into a single circle, into a single ring. And then actually the area of that ring depends only on the radius, because you have this r as a distance and you have also dr, which is the thickness of this ring. So I can replace this dA by 2 pi r dr, or which is equivalent by pi dr squared. So I go not from capital A to small a. I don't just make a literally replacing just capital A by small a. As you see, if you look at this formally, I replace dA by pi dr squared, and I also replace capital A by 0, and I also replace something which is non-existent here by small a. What I actually do is, instead of integration of the area, I integrate of the whole disk by switching the radius from 0 to a. So I go in my radius changes from 0 to a. The a is the whole radius of the disk. Okay, so this is how I go in this problem. The next one is 2.2 and 39. Let me see. Well, it employs these formulas again, but it mixes some thermodynamics and molecular physics together. So it's just, I can consider this problem quite an unrealistic one, because nowhere you are going to solve this kind of a problem. It's just a problem to check your knowledge of these equations and what polytropic process is. So it just combines two different concepts together. An ideal gas goes through a polytropic process. Polytropic processes were the topic of our discussion on the first lecture, probably. If you have forgotten, for example, what polytropic process is, it's a process in which gas has a constant heat capacity. And as we have derived for the ideal gas, the equation of this process is pressure times volume to some constant power n is constant. So if your ideal gas undergoes this process, and if for this gas you know that Cv is constant, it's also important, then this is a polytropic process. In this process, the heat capacity on the gas would be constant. So that's the polytropic process. So and this one is called polytropic exponent, and it can be any value. It can be positive, negative, and it also can be infinite. When it is infinite, then what it actually means that volume remains constant. So when it's infinite, it actually doesn't matter how your pressure changes, the volume remains the same. So the infinite polytropic exponent means that you have an isochoric process. Okay, find the polytropic exponent n if in this process the coefficient of diffusion A remains constant. Okay, diffusion is constant, diffusion coefficient. And as we know, the diffusion coefficient is 1/3 times lambda times mean thermal speed. Okay, of course, these quantities are all about some microscopic events, so we need to relate them somehow to pressure, volume, and temperature. That's quite easy for the mean thermal speed, because the mean thermal speed is proportional to the square root of temperature multiplied by some constants there, which actually don't matter here. So, well, yes, thank you. So in here we have temperature multiplied by some constants, so square root of T. But these constants can be neglected when we consider the dependence of all of these on thermodynamic variables. At the same time, lambda is approximately 1 square root times n times sigma. Okay, sigma, a collisional cross-section, is the constant. It depends only on the material. So it doesn't change when you change pressure, you change temperature, sigma remains the same. What actually changes is the number density. And number density, as we know, P equals N kBT. So number density is proportional. Number density is proportional to pressure over temperature. This one is proportional to number density in the power -1. So collecting all of that together, we get that this is proportional to temperature over pressure, this comes from lambda, multiplied by square root of T. So essentially, the condition in this problem means that T to the power of 3/2 divided by pressure is constant. Well, we know something about temperature, but we need to go to volume. And, well, volume, as we know, PV equals to RT. So volume is proportional to the product of pressure. The temperature is proportional to the product of pressure and volume. So I can replace T to the 3/2 by PV to the 3/2. And if I divide by P, I would get P to the power of 1/2 multiplied by V to the 3/2 is constant. Okay, it's almost looks the same as we want, but only one operation remains. If we have some value which is constant, then if we calculate the squared of that value, then it would also be constant. So if I calculate squared of this, that would be constant squared, and that is constant. Then, well, if I do this calculation, I would get that PV cubed is constant. So my polytropic exponent exactly equals to 3. So that's when we have the diffusion coefficient constant. Well, finally, we also have viscosity and heat conductivity. I would like to combine them into a single question. As follows from the equations for the viscosity coefficient and thermal conductivity coefficient. Thermal conductivity is equal to viscosity multiplied by CV, where CV is the specific heat at constant volume. And this is independent of the pressure, temperature, volume whatsoever. So that means that if the viscosity coefficient is constant, then thermal conductivity would also be constant. And finally, we also can write that this actually equals to d multiplied by rho. We can also check the formula for d, the equation for eta. So eta is indeed obtained by multiplying d by rho. So as we know from the previous solution, then the d is proportional to t to the power of 3 over 2 over the pressure, while the density, we have again, the density is actually proportional to n, and n is proportional to pressure over temperature. So, okay, pressure gets out of here. We have temperature to the power of 1 over 2, which is constant. So that means that actually in the process B and C, we have an isothermic process. And in this process, we know that PV equals to constant. So the polytropic exponent is 1. That's the end for solution. And once again, well, for the B and C, it once again reiterates the fact from the lecture that I have derived that thermal conductivity and viscosity at the constant pressure are independent from, at the constant temperature, are independent of pressure. Okay, the last one. The last one is 2.2 and 49. Uh, 2.2 and 49. Okay, let's go here once again. It says that, well, that requires you to solve the heat equation. A rod of length L in one dimension. A rod of length L with thermally insulated lateral surface consists of material whose heat conductivity coefficient varies with temperature. Now that's the difference from our usual formulation, because now we have heat conductivity as the function of temperature, and the temperature is also the function of other space coordinates. The ends of the rod are kept at temperatures T1 and T2. So let's say here is T1, here is T2. Or we can actually write that if I have the x-axis here, and here is 0, here is L, we can write that T of 0 equals to T1, T of L equals to T2, and these are called boundary conditions in the problem, because 0 and L are boundaries of the problem, and in between we solve the equation, in between 0 and L. So we know the temperature at boundaries. These are boundary conditions. And we need to calculate function T of x in the stationary state and the heat flow density. So let's say if T1 is greater than T2, then heat flows in this direction. Okay, so since we deal with a stationary problem, once again I would say that heat is not being accumulated anywhere in my rod, and that means that the heat flow is constant everywhere in the rod. So heat flow is constant. So that heat flow by Fourier's law is actually kappa multiplied by the derivative of dt over, okay, since now we don't deal with t as a function of time, we can write simply a derivative dt over dx. And well, we know that kappa is dependent on temperature, so I can write that this is minus alpha over T multiplied by dt over dx. And that's constant. So let's keep it Q. So Q is the heat flow and it's constant. Good. So we can find that the temperature dependence as a function of Q. So this is a differential equation which can be solved by the variable separation method, and I can write that dt over T equals to minus Q dx over alpha. After I integrate it, I get that actually, so I can integrate it from 0 to some point x. So I can get that the natural log of T of x over T of 0, which is actually T1, equals to minus Qx over alpha. Well, so now we know the temperature dependence actually. This is an implicit definition, so it gives you the temperature at some x using some equation, but we can determine T of x at that equation. What's missing here is that we don't know Q, but we know the temperature at L. So we can just insert L into here and get Q from that. We can write that natural log of T2 over T1 is exactly minus Q L over alpha. So that gives me Q. Q is minus alpha over L times natural log of T2 over T1. That's the heat flow. And then we can insert it back into this equation. Now that we have expressed Q as the function of T2 and T1, that's actually the answer to one part of this problem, which requires us to determine the heat flow. And as we go and insert it here, we can calculate T of x. So since it's the final problem for today, I'm going just to wipe all of these important equations from the blackboard and continue here. So now we need just to solve that logarithmic equation. Logarithm T of x over T1 is minus Qx over alpha. Okay, and we can write, instead of Q, we can write that this is minus alpha over L times minus alpha over L natural log of T2 over T1. Then alpha gets eliminated from here. Minus by minus give me plus. So altogether I have x over L logarithm T2 over T1. And then I can calculate the exponent of the left and right hand side. So that will give me T of x over T1 equals to T2 over T1 to the x over L. And finally, T of x equals to T1 multiplied by T2 over T1 multiplied to the x over L. So finally I get that this is a T1 multiplied by L minus x over L multiplied by T2 to the x over L. If you look at this, well, this is actually, well, yeah, that's the distribution of temperature in which the temperature is changing by the same factor with the same distance. So as you increase the distance by 1, then actually you slightly decrease this exponent here, slightly increase the exponent here, and that means that the whole temperature is multiplied by the same factor. So what we have here is actually the exponential dependence of temperature as a function of coordinates. And that's unusual because previously we dealt with only with the linear distributions of the quantities, but all of that was thanks to the fact that the parameter, like for example eta in the viscosity or the diffusion coefficient in other problem, were considered constant. But in here, the thermal conductivity is no longer constant, so that gives rise to really exotic distributions of temperature in our one-dimensional system. So if you don't have any questions about this problem, I think we can finish our seminar today.